Okay. So everybody are okay? As second part of class, we are continuing with the algorithms that we can use in visual Islam and visual information of the environment, how it can be used. So one of the techniques that we have and very famous in visual construction of the map is Iterative Closest Point, known as ICP. It means that, let's say we have a LiDAR scanner and we have 3D mesh and cloud of the environment. So you scan the environment, then you have 3D mesh and point clouds. Now, how we can use these 3D point clouds in order to construct the map in simplest form? We will see the basic technique and algorithm to understand it. For example, at time t, I have a scan, then time moves, t added by 1, new scan comes. Then I don't have any more the features and landmarks that I detected to match them and update my map. Then it's like everything is point and pixels in 3D. What we can do with those kind of situations? Today we want to talk about ICP, Iterative Closest Point, and different techniques. So that we will start with introduction to ICP algorithm. We talk about the known correspondences, we will talk about the unknown correspondences, and we will talk about different techniques of ICP, for example, ICP algorithm for rejection the outliers. And here you need to basically know what's happening with visual mapping for in form of 3D construction of the map. It is not only limited for 3D, we can use it for 2D construction of the map too. What does it mean? It means that if you have a map like this, and this is like in something like this in 2D, so how you can match that one with this one? So in time t, you get this point 2D map of the scan of the environment with LiDAR scanner, and t added by 1, you get that one. Then how we can know that these are same and how we can put them and have one single identical map as output. So today in this chapter we want to see general procedure of how this can be possible and how this can be happening. So first of all, if we want to determine the visual odometry, what is the visual odometry? It is the process of determining the position and orientation of robots by analyzing the visual data. It means that we don't want to rely on odometry and optocounter and motion commands anymore. We want to say, okay, I'm moving, visual information is coming to me, and I want to, using the visual information, know the robot location too. So that the algorithms that we are going to learn today not only can give us the output map of the mapping these together, but if I'm at time t here and robot moves here, this can give me some meaningful information. What is the information that this can give me? Translation, and it can give me the rotation if I can detect it, right? But this is the visual information, so that I can remap it to from visual information. If I can extract these translation and rotation and remap it to real environment, I can understand how much my robot moved in the environment. So we have some definitions that we need to have a look at the first. So first of all, we have the definition of the ego motion. Then we are talking about the visual odometry. So ego motion means we have 3D motion of the camera with one environment. For example, you can see an example here that these drawn lines show that for example, the car with the camera that is moving in toward the straight away, and here, for example, rotates to the right, and this calculation of this movement is called ego motion. That is usually and basically is coming from rigid scene calculation, and it is one of the most important visual odometry element of the robot navigation, because if you want to have robot navigation with visual odometry and visual movement, extracting visual information to control robot movement and do the navigation, for example, where is the direction that robot is moving, ego motion is one of the important elements that we have there. On the other hand, what is the ego motion estimation? We can define that it is determining the most likely transformation between previous and current sensor reading. So that the same thing, the definition, we only want to estimate it. On the other hand, transformation in geometry can be called as rotation, and translation that we already discussed it in separate chapter in detail, how we can do it in mathematical form. We don't need to discuss it anymore. The same rotation calculations that we did there now can be used for all one of these points that we have here. The mass already we studied it. So now let's say what is the iterative closest point ICP algorithms. So it is introduced by Basel 1992, is a well-known standard algorithm for visual odometry and is most often used to construct map of the LiDAR scans. So if you have LiDAR scan, the robot is moving in the environment. If you want to construct 3D map, it's very common to use ICP, but we will have different techniques. You will see which one is how generally and how they can work. So input is the sensor reading, can be as point cloud or vision, and the other one can be environment model, again as point cloud and vision. So not only the sensor reading can be as input, but also my constructed map can be input of the my algorithm in order to do the calculations too. Okay, clear? What is the output? Output is transformation that minimizes the distances between 2 point clouds. Transformation includes translation and rotation. So I want to calculate some matrices that minimizes the moving to mesh point clouds in order to mesh them to one identical map that I can have. How generally it is happening? In the general way of explanation, we can say iteratively adjust the transformation so that we can converge it to local minimum, and we can calculate the gradient descent or squared error to do that, but we will see how. So for students who studied reinforcement learning now know what is the gradient descent and what is the stochastic gradient descent, but if you don't know, just have a look at how we can optimize it. This is optimization technique that we can optimize weights to do that. So we say, okay, let's break it down a little bit. If we have two corresponding point sets or clouds, we can represent as point set cloud P and Q. That these are representing P1 to Pn, that each one of these P's are, for example, a point in cloud that can be in 3 dimension X, Y, Z. We don't have orientation for each point, just X, Y, Z. If it's 2D, X, Y. So P1 has X, Y, Z up to Pn, X, Y, Z. And Q is also same. So we have lots of points in 2 different clouds. We want to see how to find out those bunch of x, y, z's that we have in array, we can deal with it. Because when it's visual, you see, look at the visual data, you can understand this is the map, for example. But in computer, in algorithm, you doesn't know, just bunch of points over there. You have no idea what's happening. So as I told you, output is the translation and rotation, T and R, that minimizes sum of squared error to the point-to-point can be considered. Sum of the squared error, what was it? We just want to, for each one of these, like if you consider this point that corresponds to this point, we can calculate the error by the distance, right? What is the d of this distance? And this is the, we can say this is the error between these 2 points. What about next point? The error. And sum of the squared of all will be error of this and this matching. So how we can represent in an equation form? We can say the error of the rotation and translation is equal to 1 over a of the sum of the squared of the Euclidean distance of these points, considering the rotation too. So when we write in this form, it means that we have, in math we can write it in this form too, to the power of 2, that it means the square of the distances between each one of the identical points, that they have translation and they have rotation. This is point set 1, subtracted by rotated second cloud point and translation. So first point set, rotated second cloud, and the translation, the distances can be give us the error of the rotation and translation of 2 3D point clouds. I noted some points for you here that we can define index I with point separately too. But the point is here, you should quickly realize that this I, these are separate point clouds, right? Do we know this I? So if they are separate point clouds, even though if they are meshed together, if you don't know this I, and these are meshed, like these are like randomly in the point cloud, then the difference is still, the error will be high. Although you may have a map like as P here, and the Q can be like this. And if you don't know that I, it means that although the map that really you have is looking like this, but the point that the error that you're calculating, if you don't know the I, then they may be this point of blue one, instead of be compared with this one, will be compared maybe with this one over here. And this can happen all the time over there, then that can be problematic also. So that's one point that we, for simplicity, we can consider we have known correspondences, for example. On the other hand, we also can add the weights to the correspondences in each one, indeed. And we can say how likely that correspondency and the difference is more important. What does it mean? It means that how certain I am that this point is this point over here, not this point. The features, the point clouds that are more, I'm more certain that are the same, I can say they have more weight to measure my error. Clear? With adding weights to the point cloud. So we define the weights matrix of the W's, and we can put it on the calculations. So here the main objective is find the best parameters for transformation. That is for best alignment, as we said. In order to do that, we need to also have a look at, we have different techniques. One of the techniques also that is common to use in iterative closest point is SVD, that with known correspondence is how to calculate the transformation. and it's actually estimating, if we don't know the correspondences, how to calculate the transformation. But let's have a look at the first of all known correspondences for ICP iterative closest point. So we say if we know exactly which point is which point, if I know the correspondences which point is which point, then I can do just mass calculation to minimize the error. How? I already learned how to do transformation and rotation. You know already. Then you can do apply. If you know which one is which one, then you can move it, right? Move it, put it there mathematically. One of the ways also to do that is SVD, that we will see. So what happened here? Okay. So we say when correct correspondences are known, rotation and translation can be in closed form, so that we can do it. It is called closed form, and in order to do this, for make it faster, we can apply calculation of the center of mass of both point clouds to make it simpler, and do the rotation and transformation. It means that if you have point cloud A and point cloud B, the easiest way to merge these together, first of all, is to calculate the center of mass. If you calculate center of mass of the point cloud A and center of mass of point cloud B, then you can translate center of mass of point clouds, instead of moving each one of the particles, each one of the point clouds. Then you can move center of mass, but they will be like not matched together. Then you can rotate it. So how we can do that mathematically? The point cloud P can be calculated the center of mass. This is simple equation to calculate the center of mass, 1 over the average of the weighted sum of them, then times the sum of the each point cloud times the weight one. We calculate center of mass for P. We calculate for Q. Why the weight? Because in center of mass, the weight is also important, right? If you want to calculate my weight, my center of mass, my weight is important. W is important over there too, because of the weight of each element. So that what is happening, we are minimizing the differences between the P and the Q of center of masses, minimizing the distances between these. So that it means that if this is point cloud, consider this is just one point cloud, and like scanning of a wall in 2D. There is a wall or a shape like this, A and B. Then what's happening? We calculate the center of mass, and we would like to translate it to have it. But this translation is simple. We can translate, but we have a technique called, as I mentioned, SVD. Its name is singular value decomposition, that helps us in order to do that. It is a standard mathematical procedure for decompose a matrix in 3 different matrices, and as you can see here, we can do the process like this. From this shape, from this one, we want to achieve this one. So H is what we want to achieve. From this to this, to applying the rotation, and even we can do the scaling too, but for simplicity usually we say, okay, let's ignore the scaling. So what we can do, we can mathematically decompose it to these 3 steps: V transposed, sigma, and U, that each one is in charge of doing different things. For example, this is simple rotation at the beginning, and this is like doing this scaling, and this is final rotation. So we say, okay, we have an initial vector Vt, this one, then scaling of the sigma, as I explained, and final rotation. So this is called singular value decomposition. That what we do. First of all, we find out the H, what we want to achieve. From here to here, we want to find the H. That finding the H can be the differences of this. You can consider this is a point cloud, this is another point cloud, and to calculate the differences, what we want to find, this is the H. That H can be calculated as a cross covariance matrix simply. That is the differences of these 2 point clouds times the weights. That can be called cross covariance matrix, that finally this H indicates what we want to go. From here we want to go there, so that we can write SVD of H. Now SVD of H should decompose into 3 to achieve it. Got it? First find the difference, then apply SVD of the difference. Then this can be shown in 3D matrix U sigma VT, so that we can achieve the rotation. The optimal rotation can be R equal to UV transpose. Basically, for simplicity, we ignore the scaling, then we can scale it too. And translation, of course, is simple. For translation, we don't need to do something complex. We can write the point cloud subtracted by rotated point cloud. Then you have the translation, then you can translate it. I put the, I didn't prove this, how mathematically can be proven for SVD, for example. I put the original paper, that is IEEE transactional pattern analysis, that shows how, proves exactly how this mathematically can be applied. But in Python, we have libraries that can do this already implemented in 1-2 lines. All the calculations can be done for us. So how it looks like, as I explained to you, let's say we have point cloud A like this shape and point cloud B like that shape. So what is the objective? Their coordinate, their positions are different. We are matching them together, like as you can see here, with applying translation and rotation. Of course, there is no optimal solution to do this, because this is NP-hard problem. Lots of loops should be done to do this. But the basic idea, the simplest idea, find the center of mass, move it, then rotate it by finding the differences, by knowing correspondences. Of course, you need to know the correspondences, find the differences, calculate the SVD, then rotate it. Is it clear so far? General flow. Okay. So whenever you're hearing about the, we are talking about the ICP, iterative closest point, in the simplest form, consider we have 2 point clouds, 2D or 3D. Find the center of mass, then bring it, translate the center of mass, then rotate it to match it. This is the simplest understanding. I will also run some examples for you today if you have time. So now we can say the idea is generating estimations or guesses, kind of, to make this procedure as accurate as we can if we don't know correspondences. What does it mean? It means that, okay, if we know correspondences, as I told you, calculate center of mass, move it, rotate it. But if we don't know correspondences, then how you want to calculate the error? How you want to calculate this over here? This calculation, where was it? How you want to calculate this H over here? Because this says, okay, the covariance matrix of the differences of the ice elements, and you don't know it. Then how you want to calculate it? That's difficulties with unknown correspondences. That what we say, okay, we say the idea is guessing. Try to guess which one is closer, and with ICP, iteratively guess it. Guess, and try to move guess to finally to have some result. And then after you guessing, actually, I'm guessing that maybe like this point is related to this point, and if I move, let me remove this, is a bit complex now here. Okay. The idea is, consider this is just one. I'm not removing the other one. So the blue one, if I guess this one, that is this one. Wrong, right? that should be this one. But I'm guessing that one. And if I move it, it comes closer, right? Kind of a step forward. It is better than the current one, although this map will go somewhere there. But if I'm not doing just only one guess, I may do many guesses. And by average, if I bring it closer, then if I do that in iterative guess, it can finally give me what I want. And let's see what techniques we have to do that. So as I told you, we iteratively can do that. We assume that the point clouds are in the same coordinate system because we don't want to make it complex. For example, the robot is moving or something. So now we need to find correspondences. How to do that guesses. So one of the technique is as it's named over here, iterative closest point is finding closest point. We have this point cloud A, and this is point cloud B. Robot is moved, and it scan A, scan B. Okay. Then the closest point says, okay, for this point over here, what is the closest point of other cloud? Minimum closest point, maybe this point. For this point, what is the closest point of the other cloud? You measure the distance, this is the most closest. For on the purple one, this one, what is the closest point? Maybe this one, this one, this one, this one. You calculate by all of them or some of them. That we will also discuss. There are different techniques for that. After you calculating these minimum distances, now if we calculate the SVD to just translate and move it, rotate it by these ones. That these points that we find are guesses that we have, and the guesses in order to do matching. So now let's have a look at the pseudocode, how the steps are looking like, or algorithm. Step A, associate points to the near neighbor, calculate then the information, that the transformation of minimizing the error, then transform points using the estimated parameters, then if the stopping criteria are satisfied, then return the calculations. Because at first step, you may apply these guesses and do the translation and rotation, but maybe still you will have error at first step. This move closer but not match completely. Then you guess it again. Then you, per each sum of these points, you say, okay, find the closest point again. Then you will see that it is adjusting. And with some threshold that you say, okay, when I achieve that threshold, then I don't need to continue anymore. This is called iterative closest point, and one of the strongest algorithms that can give us chance to guess 2-point clouds and move them and adjust them. Question? Any question? The flow, all of you at least should know now. Okay. The idea is simple. Now, visually, let's have a look how it looks like. So if we have that one as 2-point clouds, we guess. Then we come here at iteration 1. So we apply SVD to translate and rotate. We achieve this one by these matchings. After that, I do guessing again and finding that lines again, which one is which one is which one. Iterate one more time, a bit closer, do it again, matching, do it again, and you see that it is matched, for example, in this example, 100%. Iteratively finding closest point and match it to finally achieve the final map. And in 3D, how it looks like? In 3D, we can do this example, as you can see. Here, we have point cloud A, we have point cloud B, as an example of, for example, a chair, part of environment. Then after some iterations, and final iteration is completely matched, iterative closest point. And I think I can show you over here some implementation of that guy that I have in the slides. With Open 3D, let me see. I ran it today, I guess, in the morning for you. Ready. Yeah, we have the 3D point clouds. You can see point cloud A, point cloud B. They are randomly rotated and randomly translated. So these are same point cloud, because I didn't want to use two separate ones. Same one, but I randomly moved it in the environment. They can be separate scans of the environment. But after applying iterative closest point, give some time to my computer. Then you can see that we have matching like this. So I did it by purpose, adding some, changing some parameters that is not matching completely because it's not visible. But yeah, you can see that after applying some iterations, it came closer. And if we continue iterations with good thresholding, we can achieve high accurate point cloud matching, so that your robot is moving, scanning in the environment. Every time one of these ones come, you have one as reference as map that you have. New one comes, you merge it. New one come, you merge it. New one come, you merge it. Then you can construct the map of environment in 3D. But the resolution is very important because this is costly. If you are calculating many points, the accuracy is higher, but then it's slower. Then you need to sample how many guesses of the point cloud to take, and based on how many guesses, then do the iterative closest point. And we will see today some techniques that make it faster. So yeah, here second iteration, not too much differences because I make it not too accurate, but in the slides you can see that here I showed the accurate output. So this is also very applicable in different applications. Like you can see, this is like real sense, and it can be used in CAD models in this video that they are using for scanning solid object 3D shape sensor by 3D shape sensor. So they have this camera which gives the depth, and this is the object that they have. With ICP, let's see how they can have the shape of that object. I mean, we are not limited only to have it in SLAM, also can use it in different algorithms. So that's the scan that it is the output of the sensor. Then ICP matching, you can see that when it shows it again, it matches to the map that it has already. You see, this is the general map that this new scanned data will be plotted and mapped on the previously known one with the same idea. And here you can see another representation form of the same idea. And even with the rotation, you see that constructed map is the same. It's perfectly doing the algorithm, putting some marks to make it more difficult. I mean, the scan will be changed, and you can see that in heat plot that part is a little bit not visible over there. And the point is the distance wherever it is, the rotation wherever it is, it can plot it, map it in online form quickly as it is possible. Then they compare two different ones. They are different a little bit in terms of shape, you can see. and they show the CAD model of the objects for applying ICP. And now they apply for both together. And they are different model. You can see that says here and here this part are different. And after applying the that one, you see that this one is also there or clear. The other parts can be matched because very similar. The parts that are similar can be matched, but this part over here, you can see that is also identical and is not matching that well. This one is matching very well, but this one is not matching very well. But the part that is matching will still moves to the shape that is known. And here, I guess, new unknown one is coming. Then a couple of examples to see if how our ICP is working. Okay, I put the link. You can watch something similar. But what are the important elements that we need to know about? Performance of the ICP is like speed and stability is important, trade-off between the stability and speed. If we use more point clouds, we have more stable construction of that, but we lose the speed. And tolerance on the noise, how much it is, that is related to that, and how far distances between two points cloud can be depending on the data and application that we have. On the other hand, we have different variants of the ICP, not only the one closest point. One is like A, selecting and weighting source points. B is finding corresponding points. Another is rejecting certain outlier correspondences. Another is choosing an error metric, and finally minimizing. That quickly we will look at each one of these now, how they look like in briefly. So first of all, if we talk about the selecting and weighting source points technique, we say that we can use all points or we can use random sampling. If you use all points, of course it's clear that's very heavy, but random sampling says, okay, uniformly randomly sample from your point cloud. Depending on how much accuracy you want, you can see the density here. That to do that, the step C is especially uniform subsampling, and step D or type D is feature-based sampling. For these two, we discussed it. This is clear. Random sampling is there. But what about the three, especially uniform subsampling, especially uniform subsampling means that there are some challenges also. For example, density of point clouds are different. So the scan that you have, the density here that is close is higher than the density that is far from your object. And when your robot is moving, or if you have a car or robot, whatever that is it, and moving, then you have a different set of point clouds with different densities, that you don't have uniform distribution anymore to use the technique that we have there. On the other hand, that you should consider it like here you have less point clouds, and here you have more, and your robot from there moves here. Then from same scenario you have more, so that it is like then also the scale is different. You see this one in point cloud from far. When you come here, it is the same, but everything is changed. So that's called the especially uniform subsampling, that you need to also be aware that it is existing. But ICP usually is doing well if you tune parameters well. Then we have the feature-based sampling that we already, I think, discussed it well. But next lesson we will also see one advanced technique to do that. using additional information like edge, curves, colors of the environment that can increase efficiency and accuracy and requires pre-processing technique. For example, we can see this video over here that is kind of similar to what you do as homeworks or projects, that you can see in this video. This is the robot that's moving in the environment, and the LiDAR scanner. The scans comes from the environment, and ICP has been implemented. When, like in 2D, you can consider this is the point cloud that is coming, and in online form, the same example code that I ran, you can run it. Similar idea, and match the environment, and you will have online construction of the map in this form, so that you can merge it to general map. But of course, you will have challenge of like closing loop. You have challenge of the error on the control command. That also should be dealt with. But still, now we have very strong tools to deal with the 3D mesh cloud. So that was number one. The number two is finding correspondences of the points that we have closest point matching technique. That is like the idea is finding closest point in the other point set. That is, we can say we can have thresholding. That it means that if you have a point A, don't match it with very far ones. Match it with somewhere close by, so that kind of. So before making it complex, let me tell you. This idea also used in some other ones, but says, okay, thresholding says you have a map like this, and you know that next scan is impossible to jump somewhere far, will be somewhere around here, right? Your scan A, time increases, impossible, basically by default we say impossible to jump to another building or somewhere else. I'm somewhere around here, I'm moving somewhere around here. Then I can put a threshold that say, okay, when you're matching the features, match features to nearby point cloud. The idea is coming from there, and this is called closest point matching technique. That this technique can be boosted because it has speed problem, and to deal with the speed problem, we can create k-dimensional tree that is known as KD tree, that is based on the binary search tree, that we say each one of these points can become from the form of the KD tree, that this KD tree is famous. How to construct it? You can use binary search tree to construct it. After you construct it, the searching and matching the correspondences is very fast later after constructing this KD tree. It's a technique to boost up your finding correspondences. Another technique is for finding correspondences is shooting-based approach. That shooting-based approach says, okay, if you want to have a guess, if you want to guess this point, shoot. What does it mean, shoot? It means that shoot a line. Whatever it is, although it is wrong, shoot. Then shoot like many of these, then try to match it. So although we may have lots of error, how we can shoot, like, but that shooting is like a Spider-Man. Then bring it closer. Then do it again. Bring it closer. Then this is a technique called shooting-based approach of ICP. So we are looking at different techniques of the ICP, not only the closest point. Other one is the projection-based for finding correspondences, projection-based matching technique. Projection-based says that, okay, if your LiDAR scanner is in point A and moves to the point B, the line of projection that moves, moving like this, then the projection should be, the guessing should be at the same direction. You can construct a visual visual line that where is the moving direction and where is the moving, then you can continue that one on the matching. Then all of these lines should be matched like this, because I have this information. Then more likely I have better guesses. So this is called projection-based matching technique for ICP. We have third one, that is rejecting certain outlier correspondences, that is ignoring some of the points based on different techniques. One can be distance, one can be the weights, one can be different elements that even we can use learning algorithm to find it. What does it mean? It means that we have point cloud A, we have point cloud B. Here you can see in point cloud B, this part is missing, we don't have it. We call it outlier and we want to drop it. Don't guess from this part. Because if we guess from this part, since we don't have it in the second point cloud, this will cause error, right? If we guess from this one, we cannot match it. We should match it to something wrong, most likely. And if we can put outlier, it means that if we can understand and remove this information, then our guesses will be more likely correct for iterative closest point and bring it to the matching. So that one is thresholding with simple distance. Another one can be like learning algorithms and techniques. And there are many different research on this, and this is also open problem that you can choose as continue to work, even can be a paper publication if you can do it well. And I think Ugo is doing something similar for his research with outlier detection for Orbislam, that kind of trying to do this. But this is for ICP. So the fourth one is the error metric, that the error metric of the ICP can be point to point. We discussed already with just error of the distances of the 2-point clouds, square error. But also we can have point to plane error. That is very nice idea. Instead of point to point matching, we can assign individual covariance for each point to the plane of the other cloud. If this is the one cloud, then if I pick one point, then I can find the error not only to one point that maybe I have lots of error. I can calculate the error based on this plane, not just one point. So that how can it possible? If you can do that, this is the paper that compared this. I found out, I was searching for this part of class to find implementation that compares these two techniques and says, okay, if you have point to plane and if you have standard ICP and if you have the point-to-point calculation, you can see that the point to plane is green. One is doing better than the this red one, that is point-to-point calculations. And the blue one is a technique that let me see, the blue one or green one, standard. Yeah, this is error. So the green one is the point to plane. This one is point to point as a standard ICP. And this one is the generalized ICP that they propose the technique to also improve these two and publish it over here. I'm not going to explain it. If you are interested in, go study the paper, how you can even improve this point to plane technique in order to calculate the error. And finally, we have minimization. That minimization says, okay, using nonlinear minimization algorithms can be useful over here. For example, gradient descent. If you remember, in, for example, neural network, gradient descent were helping us to calculate the weights to minimize the error. And here we have something similar problem. Then gradient descent, for example, can be applied to do the same thing over here. So fancy imagination of the bringing another algorithm from another world to solve this problem. And Gaussian Newton is another technique that if you are interested in, you can study how it is working. It is like solving some problems of the nonlinearity over there with some mathematical equations. The question is, does the odometry have advantage for visual SLAM to be used there? Of course it is. We can use odometry pose estimation to improve ICP by giving the knowledge of movement of odometry to the visual odometry to improve it. But of course it can also calculate it itself, so that if robot from A moves to point B, this is robot, I better to put the LiDAR scanner on top of it, but this is LiDAR scanner, then moves 2 scans, then this line, this odometry information can be helpful for me to also construct the map. As we saw some algorithms, and if we want to summarize and conclude, we say ICP is powerful for calculating the displacement between point clouds. ICP speed is depending on the number of points that I'm choosing and how to match them together. And basically ICP is locally optimal, because if the map is too big, just calculating the center of mass is not enough. Maybe it rotates it, but wrongly, in wrong direction, with some mismatching, so that it is locally optimal. Okay, so that's it for today. If you have any question, you can feel free to ask.